All right, I thought I was done with this previous example, but I guess not. There's a part C. Assuming that the score of each student is independent of every other student. If you select 4 students randomly, find the probability that at least one of the 4 scores above a 90. So this is a probability that one kid scores above a 90. So I want the probability that at least 1 in 4 score 90 plus. Well, there's a lot of ways that you can score that 1 in 4. You could get one kid that scores a 4. It could be the first, second, third, or fourth. 2 kids could score over a 90. It could be the first and the second, or the first and the third, or the second and the fourth. There's a ton of different ways that 1 in 4 kids, at least 1 in 4 kids, can get over a 90. However, there's only one way that the complement of that happens. The complement of getting at least 1 is getting no 90 pluses in 4 kids. So nobody gets over a 90. That only happens one way. The first kid's got to not get a 90. It's the complement of 0.231. The second kid times the second kid times the third kid times the fourth kid, and as long as we have independence, we can just multiply those 4 together. That's just that. So 1 minus last answer to the 4th. 65%. Okay? It's a review from chapter 5. This is all review. Well, we got transformations, which is kind of a review. We got normal models, which is a review. And we got some probability, at least 1. All review, kind of putting it all together. All right, this is what section 6.2 is really about, combining random variables. Not doing a linear transformation on a random variable, but combining 2 different random variables together. So first we need to talk about independent random variables. So let's kind of look at an example. You can read the definition if you want, but suppose we randomly select a male from the US male population and select a random female from the US female population. If we let M be the male's height and W be the woman's height, are M and W independent events? So the question is, if we select this guy and let's say he's tall, is that going to somehow influence the girl's height? Because we're selecting the girl separately from a completely different population, this guy's height should have no influence on her height at all. So we would say yes, these are independent. The guy's height has no influence on the girl's height. Now let's randomly select 1 two-gender married couple in the US. So I'm going to select one couple, and I'm going to look at the guy and the girl combination. If X is the guy's height and Y is the girl's height, are these independent? So this is going to be no. If the guy is taller, perhaps a taller guy in a married couple, maybe a tall guy is more likely to marry a taller girl or a smaller girl or something. I don't know. I think taller people are kind of generally marry taller people. So if we get a tall guy that may, not sure, but it may, probably will influence the I'm trying to we get it. I think I want to say this a little bit differently. I'm sorry. I mean, that what I was saying was fine. It just I kind of wanted to word it a little differently. I think I would just say perhaps taller guys tend to marry taller girls. So, and what really makes it not independent is I just selected one couple. I didn't select two independent people. You know, there's a link between these two people. They married each other. You know, they're not. It's just I didn't independently select them. So why is this important? Well, we are going to calculate the sum of two random variables together now. Okay. So if x and y are random variables and t is going to be defined as the sum of those two random variables, then how do we find the mean of t and the standard deviation of t? Well, for the mean of t, it doesn't matter if they're independent or not. We don't need independent here. Just FYI. So how do we find the expected value? Well, the expected value is just what you'd expect. If you want to add the two variables together, you just add the expected value of the two variables together. The expected value of t, of the total, is the expected value of x plus the expected value of y. Means are always easy. Standard deviation, not so easy. First of all, we must have independence before we can use this formula. That's why we talked about independence. And we do not add the standard deviations. Instead, we add the variances. The variance of t is the variance of x plus the variance of y. And I'm not going to prove this. You don't need to know the proof of it. I'm not even really 100% sure what the justification would look like, so let's not worry about it. That's it. Add the variances. This is why variance is actually kind of important. So note, you never add the standard deviations. Instead, you add the variances only if the variables are independent. Just be careful about that. This is a really common mistake, and I hate writing it down, but the standard deviation of t does not equal the standard deviation of x plus the standard deviation of y. Not in general, anyway. Sometimes we think of this as the Pythagorean theorem of statistics. You know, c squared equals a squared plus b squared. You know, the sides of a triangle. You don't add up the two small sides to get the third side. You add up the squares of the two small sides to get the square of the big side. So if you want the big side, you gotta square root that. If you want the standard deviation, you square root the sum of the variances. Theorem: if two random variables are normally distributed and independent, then their sum or difference will also be normally distributed. Now, this isn't a trivial idea, but and it should be proven and justified. However, I'm not going to prove it. Just understand that if you have two variables that are normally distributed and they're independent, then their sum and differences will also be normally distributed, so we can use that normal model to make calculations. Okay? All right, I'm going to stop here, and we'll do the example in the next video.